Hi, and welcome to Lecture 17 of Applied Machine Learning. In Lecture 17, we are going to start our first topic in unsupervised learning, which is going to be density estimation. So I'm going to introduce a few useful concepts that we will need to solve this problem. Then I will define what density estimation is, and then I will define a few first methods for doing density estimation. And to begin in this part of the video, I would like to start by talking about probabilistic models in unsupervised learning. So in earlier videos, we looked at probabilistic models in the context of supervised learning, and now I want to introduce them in unsupervised learning as well. And then this is going to be, the probabilistic models are going to be the tool that we're going to use to perform density estimation. And we're also going to use them throughout all of our other lectures on unsupervised learning. So let's define probabilistic models. And just to set the context again, we are talking about unsupervised learning, which is a regime in which we have a data set without labels. And our goal is to have the algorithm look at this data and learn something interesting about it, learn something interesting about its structure without relying on human supervision. And when I say something interesting, this means things like clusters or outliers or useful signal within noise, perhaps human speech within white noise. This kind of structure. And in our earlier video, we defined the general setup for unsupervised learning. So our data set now consists of vectors of features or attributes, but we don't have any labels. And we assume that these features come from a data distribution, and they're IID samples from this data distribution. And then we define a concept of an unsupervised model, which is some function which maps inputs to interesting components, to interesting structural components, perhaps clusters or low-dimensional representations. We're going to see a lot of examples here. And of course, as usual, as in supervised learning, our models are often parametrized and they have these parameters theta. So when we talked about supervised learning, we also made a really similar assumption. We assume that data is coming from a data distribution, and one interesting modeling approach is to parameterize a probability distribution and fit it to approximate the true data distribution. This is what we did in supervised learning, and this is what we're going to do in unsupervised learning as well. So we will assume that a probabilistic model is a probability distribution over the space of attributes, and we will try to approximate our data distribution with this model. And as usual, our model may have parameters. We denote them by theta, and we use the following notation: p subscript theta to denote a probabilistic model with parameters theta. So before I go further, I just want to take a step back and talk about why probabilistic models are interesting. So we saw different types of models. We saw in supervised learning, we saw both non-probabilistic and probabilistic models. Often they're equivalent probabilistic models to non-probabilistic ones. And here in the context of unsupervised learning, we also have these two approaches. So imagine that we're trying to fit a model, a probabilistic model P to our data. What are all the interesting tasks that we could try to solve with it? What are the interesting uses that it could have? So if we fit a distribution, then we, with some additional some additional techniques and algorithms, we can draw samples from this distribution. So we can use these models to solve generation problems. For example, we can generate images of human faces from a distribution of faces that we have learned. We can also use them to find interesting structure in data. So if there are clusters, then we can ask our probabilistic model to, we can inspect our probabilistic model and we can try to recover these clusters. And perhaps the most general task that we could do with a probabilistic model is to try to learn the data distribution as accurately as possible. And this is the third task here, and this is the definition of the task of density estimation. So our data distribution here places some weight on different parts of the space of x's, and we are going to try to learn a model that also places the same weights or probabilities to the space of x's that we consider. And if we do that, if we find a probability distribution that has the same structure as our data distribution, then we say that we have accurately estimated this density. So the problem of density estimation is the problem of approximating the data distribution. And also, it's a very general task, because if we can approximate the data distribution, then we can solve all the other problems that we may want to solve, such as generating samples or representation learning or other tasks such as clustering or outlier detections. If we have a good model of the data distribution, we can solve all of these problems. And so in that sense, density estimation is the most general approach that we can solve. And in this lecture, we are going to look at a few ways in which we can do this, and we are also going to be looking at various forms of data of density estimation in subsequent lectures as well, but they will be applied to certain practical problems such as clustering or dimensionality reduction. So if our goal is to approximate the data distribution with our model, well, we need to start by defining some notion of distance between distributions. And in our earlier discussion of supervised learning, we have seen the Kullback-Leibler divergence, which is a measure that is widely used in machine learning and in mathematics and in information theory to perform exactly this comparison between the two distributions. So this is also what we're going to use in our example here. Before I start using it, I just want to remind you a few properties of the Kullback-Leibler divergence. So it is always non-negative, and it equals 0 if and only if the two distributions P and Q are equal. So this is what makes it a useful objective to optimize if we want to approximate P with Q. If we want to choose P and Q that are similar, then this is a sensible optimization objective. This is a short proof. I briefly mentioned this in the video where I talked about supervised learning. So if you want, I will not talk about this proof more in this video, but you're welcome to go back to the earlier videos if you want to have additional context about this proof. And then also an interesting feature that we have seen is that it is asymmetric, which is why we call it a divergence and not a distance between distributions. So if we were to use the Kullback-Leibler divergence to approximate the data distribution with our model, we would be optimizing an objective of the following form. Here I'm just writing the form of here I'm just using the definition of the Kullback-Leibler divergence in the first line, and then I expand the log in the second line. And you may notice that the first term here depends only on the data distribution. It does not depend on our model, and therefore we're only interested in the second term, which is the log likelihood that we have seen before. Again, this is the similar derivation. This is a similar derivation to what we did in our video on supervised learning, but I just want to remind you here how this argument works. And therefore, if we want to minimize the KL divergence, we may also maximize the likelihood, the expected likelihood of our model, which is this objective here. It is simply maximizing the expected log probability of the data under our model. So we have talked about some properties of this process, and in general, this objective here is not tractable in the form that it's written here, because we do not know the data distribution and we cannot therefore perform this expectation. But however, we have samples from the data distribution, and therefore we can use the Monte Carlo principle to approximate this expectation with expectation here with the empirical log likelihood, where we have drawn a random data set of d points, and this is simply our usual log likelihood objective that we would maximize. So again, here I have briefly re-derived the principle that we have seen earlier on our lectures on supervised learning, which is that of maximum likelihood estimation. And you can see here that the same principle, only with slight modifications to the notation. I have just replaced p of x of y with p of x, and the same reasoning can be used to derive the following maximum likelihood objective for learning a probabilistic model. And let me briefly show you again an example of how this principle can be applied. Imagine a simple example where we have a probability distribution over flips of a coin. So let's say we have a coin, and this coin has some unknown bias. It has a certain probability of falling heads and a certain probability of falling tails. And we have thrown the coin 5 times, and we have seen 3 heads and 2 tails. So we can assume a particular probabilistic model, which is the following. It only has one parameter, theta, and that's the probability of falling heads, and the parameter of the coin falling tails is 1 minus theta, and then our data set is 3 heads and 2 tails, and the likelihood of the data is simply the following by the definition of our model. And now we can look at the likelihood of the coin. We can plot it as a function of the parameter theta, and as you would expect, the principle of maximum log likelihood chooses this is the likelihood function, and the likelihood is maximized when theta equals 0.6 or 60%, which is reasonable because we have 60% of heads in our data set and 20% tails. So this is just to remind you of how maximum likelihood works, and this is an application to a simple problem. So in summary, in this video, we defined what is a probabilistic model, and we derived an objective function that can be used to learn any probabilistic model, and this is maximum likelihood. And this maximum likelihood for unsupervised models, it is simply a small modification to what we have seen for unsupervised models. And now in the next few videos, we're going to now apply these principles to perform density estimation in interesting classes of models.